Hey everyone, welcome back. So today we'll be discussing about what is mean by polynomial regression. Okay, we already discussed about what is mean by linear regression, multiple linear regression. Okay, so just once recall it. So in simple linear regression we only use one sim. Okay, simple linear regression we will use only one feature. Like the data set only contains one feature. Okay, it only contains one feature. In multiple regression it contains more than one feature. Okay, more than one, but the common thing in these two regressions are the both algorithms works on only linear data. Okay, only works on linear data. Okay, what is mean by linear data? Okay, so let us suppose let us suppose you have a data which looks like this. Okay, we can draw a straight line, so we can get around 90 to 80 accuracy. But if the dataset contains the data points as this, okay, here when we use linear regression or multiple linear regression, the plane or the line will be a straight line, right? It will, the accuracy will be compromised. It will be around 50 to 60. Okay, which is not efficient. Okay, so to overcome these kind of technique, these kind of data sets, we introduced polynomial linear regression. Okay, polynomial regression, sorry. Okay, what here, the polynomial regression works on the degrees. Okay, let me tell you the equation. So y equal to mx plus c. This is linear regression. Okay, y equal to beta naught plus beta 1x plus beta 2x 2. Okay, this is, and so on. This is multiple linear regression. So the polynomial regression looks like y equal to beta naught plus beta 1x plus beta 2 x square plus beta 3 x cube and so on. The number of degrees here, this is 1 degree, this is second degree, this is third degree. So the number of degrees is a hyperparameter we must provide to our model. Okay, so here let us suppose you have this kind of data. Okay, if you uh, the degree is most important. Like a degree in the polynomial linear polynomial regression is very important, because as we, okay, let us suppose a data set need a 2 degree polynomial regression like formula, but if we use 4 degree in the place of 2 degree, then it overfits, right? Like if the, okay, let me show you a visualization. Okay, this, so these two are the outliers, right? Okay, when we use 1 d, okay, one degree, sorry. So when we use 1 degree, it looks like this. Okay, the line look like this. Okay, so this is efficient because it gives around 95%. Okay, this gives around 95% of accuracy. But when we use degree 2 or degree 3, then the the line will be like this. Okay, okay, 1 minute, I will change the color. The line looks like this. Okay, because we have changed the degree, due to this the accuracy drastically reduced, right? Here it's around 95%, only two data points are missing. But here when we look into these four and these two and these four, okay, all these data points are missing, so the accuracy remains very low. Okay, so we need to provide very efficient hyperparameter, like the degree is the only hyperparameter in the polynomial regression. Okay, so if the degree is high, if high degree, it overfits. Okay, so we'll discuss what is meant by overfitting and underfitting in next video. Okay, just take an just a brief example as it works well on training data. It works well on training data, but does not works on testing data. Okay, this is overfitting. So if the degree is low degree, it is low degree, it underfits. Okay, underfit means it does not perform well in training data as well as testing data. Testing data. Oh, shit. Okay, testing data. Okay, this is the polynomial regression. So just a simple polynomial regression. If so, there are many other regression algorithm which can be very efficient on non-linear data than the polynomial regression, like random forest regressor, decision tree regressor, XGBoost. We, like there are many other algorithms which can be used in the place of polynomial regression. Okay, this is just simple, and let's see how the code will be working. Like I will show the visualization and how the code, the accuracy changes when we perform polynomial regression and linear regression. Okay, see the coding part of the polynomial regression. Okay, here I have imported all the libraries. Okay, all the libraries to implement the polynomial regression and all the matrices, and I'm using R2 score as a matrix for the polynomial regression. So here I have created the, okay, let's implement. Here I have created a data set. Okay, so y x as a, a random points that are sorted in ascending to ascending order. Okay, and each the range is between 0 to 5. Okay, you can see I have multiplied it with 5, so the x will be ranging from 0 to 5, and y as cosine. Okay, y as cosine, so y looks like a cosine curve. You can see here. Okay, so okay, I will show you in the later part of the video. So, and the next step is I have splitted the training and testing data. You can see here I splitted the training and testing data and imported the linear regression model, and I've used lr.fit with x train and y train. Okay, and predicted. So we have discussed about this earlier, like there are 5 steps: creation of data, next splitting, first is creation of data, this is entire the creation of, next is splitting, next is fitting the model, next predicting the model, predicting the testing data, and metrics, that is any R2 score or MSE, anything. Okay, these are the 4 to 5 steps that we need to require, which are required to perform any machine learning model. Okay, so I've done the similar thing. First I have imported all the libraries, and secondary I have created the data set. Okay, my own data set, or we can use any other data set which is predefined. Okay, which are available on other websites also, that like Kaggle or anything. Okay, and I've created the data set and splitted the data into x train and y train, and x test and y test, and loaded the model and fit it and predicted, and I've also implemented the matrices part, that is R2 score. You can see here we got around 0.42 accuracy. Okay, so the line look likes. So here it is a linear model, right? So the model can't capture the non-linearity. So the line that this is the predicted line, this is linear like a straight line, but the data you can see it's like a cosine curve. You can see it starts from 1 and at a point it comes to 0 and it's a move and the slope suddenly changes. Okay, but the linear regression can't capture the non-linearity. So to eliminate this, we come up with the polynomial regression. Okay, and remember, in scikit-learn there is no polynomial regression library. We have polynomial features. Okay, there is no direct polynomial regression. You can see. So I have taken the degree as 3. Okay, we have discussed about the degree. It we can define it as we required, like uh, while looking at the data we can define the degree, or we can check in the training process. Initially I have taken as a degree 3. When we take degree as 1, the model, the polynomial model works similar to the linear regression model. Okay, I will show that also. So I have taken the degree as 3 and the polynomial features I have loaded, and I have transformed the training and test data. Okay, training and test data using a fit transform. Okay, so we have discussed the equation of polynomial regression, that is y equal to beta naught plus beta 1 x plus beta 2 x square and so on, right? So the input, if let us suppose the degree is 2, let us suppose degree is 2. Okay, when we okay, let let me show you. When the input is 5, so it transforms the model, it transforms the 5 into x power 0, like 1, 5 power 1, that is 5, and 5 power 2, that is 25. Okay, you can see the here we have transformed the input into various columns, various numbers. Okay, it's like 5 is converted into 1, 5 and 25. Okay, so this is the thing that the transform will do. Okay, and next I have fitted the model. Same, the transformed x train and y train, that is fitted, and you can see the score, that is 60. Why it is less? Because the degree is very less. Okay, let, let us suppose, let's take the degree as 3. You can see the score increases. When we take degree as 4, it may improve or it may decrease. It has improved a lot. Okay, okay, let us say 20 degree, it may overfit, right? You can see 89 to 88. Okay, it may overfit. Okay, for the better approach, let's take a degree 3. You can see this is the optimal degree 3. Okay, degree 2. Okay, let's take a degree 2 and more, or degree 3 and more. Okay, so here I have created the new data set. Okay, for the visualization. Okay, you can see when we implement this, you can see the line, the it manages to cover the non-linearity of the data. When we take degree as 1, I have told, when we take the degree as 1, it it implements as a linear regression model. You can see here, see the similar line we have seen here. Okay, so this is the polynomial regression part, and here we need to, let us suppose here I have taken degree as 20. You can see the overfits, the model gets overfitted, like see, you can observe the, it is mimicking the training data, like overfitting the data. You can see it moves up. So we need to take the degree, like looking at the data points, and that's it. We need to take an optimal degree. So here let us take 4. You can see it is 89. It is the most optimal, like as far as we seen from 1 2 3 4 and 10 20. 4 is the optimal because it gives the maximum accuracy, R2 score. So here, this is how the polynomial regression works. There is no polynomial regression directly, like there is no polynomial regression library. So we need to convert the data into polynomial features, transform the data using polynomial features, and then we need to apply the linear regression. Then it can capture the non-linearity of the data. So this is the uh, polynomial regression coding part. Okay, let us see the next videos.